Okay, take two of this one. And so the phone rang, of course. And so I don't know, remember all the stories I told you. If it was a fantastic dinner, did I say that? Oh, I don't know. Who knows what I said? Okay, so here's the paper view of more examples from 2.4. In this section, we learned about the trig functions. So we have all our trig. And in these examples are the limits. So limits have returned, and so I wanted to do some examples on limits. The first thing that I wanted to tell you is that this limit right here is equal to 1. The limit as x approaches 0 of sine of x over x. If you're wanting the proof of that, then right here is where you can go to a YouTube video right there and look at the proof of that. It's not an easy proof, actually. It's pretty complicated. And you'll get to use quite a lot of trig in doing it, and the squeeze theorem. And so good news, all of those things. I'm going to throw my keys over there and hopefully not forget to take them to school tomorrow. I wanted to show you something that you kind of need when you're doing these limits. The limit as x goes to 0. And here you have sine of x over x, but you also need to know x over sine of x. And so this would be equal to, now if I wanted to flip that upside down, this would be the limit as x approaches 0 of sine of x. Oh, pencil, are you going to be out of ink? Lead, I guess. Raised to the negative 1. Right? Do you agree that if I raise that to the negative 1, then all that does is flip the fraction and I get back what I started with? So these two are equivalent to one another. And then by the limit laws that we learned in chapter 1, right? This would be the limit as x approaches 0 of sine of x over x raised to the negative 1. Right? That was one of our limit laws, that if you had your function being raised to the negative 1, that you could first find the limit and then raise the whole thing to the negative 1. And then good news, that is what this is right here, right? And that's equal to 1. So this is equal to 1 raised to the negative 1. And 1 raised to the negative 1, you can do it on your calculator if you don't believe me, but it's equal to 1. 1 raised to the negative 1 is equal to 1 raised to the negative 1 is equal to 1. So this is equal to 1. And we're going to need that one too. So the limit, and the reason that it's equal to 1 is because 1 is a special number. The reciprocal of 1 is 1, whereas the reciprocal of 2 is 1/2. And so 1 is kind of a special number. And so, but this is what we have here. So I'm trying to turn this as also equal. I said it was number 2, but I don't know. I'll call it star is what I'll call it. Because we're going to need that one too. And then this one right here, there's a proof of it as well. Just right underneath that other one that I showed you where it was, you can prove this one. This one's actually not as hard to prove. And if you like, you can check these proofs out on Khan Academy. And so I wouldn't ask you to prove these on the test. I mean, this one, just writing out the proof would take probably the whole entire period, the whole entire test. But people like to know why it's true. And if you want to know how it's true, I mean, I don't know how long the Khan Academy video is, but you can go check it out and you can watch that video. If you want to go through it with me in office hours, I'll go through it with you in office hours. And so we'll give a good chance to review it. So here, the 46, the limit as x goes to 0 of sine of x over pi x. So if I do just use substitution, I hate it when my pencil starts to get, when the ink gets, the lead gets, not ink, I know. My kids, it drives them crazy when I say that. But when it gets short and it keeps breaking or doing whatever it does, oh, it drives me crazy. So I was having that craziness. And so I had to prevent it from happening. So this would be sine of 0 if I replace. And this would be sine of pi times 0. I can't help it, I want parentheses there. So they're basically both sine of 0, and that's 0 over 0. Because the sine of 0 is 0. You can do your calculator if you need to verify that the sine of 0 is equal to 0. And so that means it's indeterminate, which means that the answer is not does not exist. It's probably not does not exist. The answer is probably some number. And I just got to go find what that number is. I don't know if that number is pi, or if that number is 57, or if that number is 834. And so anyway, okay, so here's kind of the idea of how this goes, is that in order to get a 1, I have to have, if I have a sine of x, I need to have a x in the denominator. So I'm going to start splitting this off, because this now it's indeterminate. That means work harder and try to figure out what it is. Okay, so I'm going to do this. The limit as x approaches 0, and then I'm going to put right here sine of x, and then times, and then I'm going to put right here sine of pi x. If I had an x right there, which I know I don't, but if I did have an x right there, then what I would have is I would have this limit right here, which is equal to 1. So if I had an x right there, then I would have the limit as x goes to 0 of sine of x over x. Now, if I want to put an x down there in the denominator, that's cool. You're allowed to do that. But you have to put an x in the, if you put 1 in the denominator, you have to put 1 in the numerator. So I'm going to go right over here, and I'm going to put the x in the numerator. That I just put this x right here. And in fact, I'm going to do them in purple so that they match one another, so that you know that I put them on there together. So here's the purple pen, and hopefully the purple pen has been used before and doesn't have the plastic yucky on it. Okay, great. Then, and I moved this one over here because I knew I wanted to make this, because that limit, when I find that limit, is equal to 1. So now when I want to find this limit, if I want it to be equal to 1, then whatever you have here, which is pi x, has to be exactly the same in the numerator. So if you have a sine of x in the denominator, whatever that is, it doesn't matter. And so you can do a star if you want to do a star there, but they just have to match. So in my case, I have pi x. So if I put a pi x right here, then they will match one another. And the only thing I have to make sure of as well is that out here, that this should also be pi x is going to 0, because see how this is x goes to 0, and that's sine of x, and then x in the numerator. So it should also be pi x. But I'm going to tell you this, pi x, as x goes to 0, pi times x is also going to 0. So I can add that that is also true, that as x goes to 0, pi times x is also going to 0. And so this is also equal to 1. But you can't just put pi x up there. That's not fair. So I'm going to put that in blue, but I put it in the top. The blue one was the one that had the new ink, or had the ink with the thing on it. And you can't tell blue from purple, can you? And then down here in the denominator, I'm going to put pi x. Okay. So the good news is here now, and I just want to write this out so that everyone is clear. So this is one of the properties of limits, that I can take the limits of the pieces, right? So now this is the limit as x goes to 0 of sine of x over x times, now I'm going to take the limit of this piece, the limit as, I'm going to say pi x goes to 0, and that was pi x over sine of pi x. Those have to match. I made a match. Times, and then this is going to be the limit as x goes to 0 of, now it's going to be x divided by pi x, but do you agree with me that x over x makes 1? And so this is really 1 over pi. Is that okay? Because the x is canceled out. And so by our properties, this is going to 1. This is going to 1. And this is going to 0, but it's of a constant, and so the answer is just the constant. So this is 1 over pi. And so our answer to this limit is 1 over pi. And so I said it was going to be some value. I didn't guess 1 over pi as one of the values it might be, but that was the value that it was. Does that seem okay? And I really showed all my work to make sure that, that everyone understood, what I was allowed to do and pull it apart. And so I hope that that's good. Come see me if those are tricky at first. Okay, so this one says the limit of secant x times sine of x. So when I think about secant of 0, now secant is 1 over sine, and that's undefined, is what that is. So I cannot do substitution. So right now I cannot substitute. And the reason I cannot substitute is one of the pieces is equal to undefined. And in order to find the limit of things that have lots of pieces, like taking the limit, using the multiplication property where you can split them apart if they're in a product, or the addition property in this case. But in this case, I have the multiplication. I have the product property. You can only do that if all the pieces are defined. And cosecant of x, so right here, cosecant of 0 is undefined. So that's the reason I can't do that. I cannot do substitute. So what I'm going to do is I'm going to try to rewrite it so that I don't have something that's undefined, so that I can substitute, and then I'll see what I have. So I have the limit as x goes to 0. And we had a problem like this before where this happened. And I think it was secant of pi over 2, I think it was. And that's undefined, if that's undefined. And what we did was we rewrote it using sine and cosine. So I'm going to do that here too. And so I'm sure that you guys remember, I'll write it up here, that cosecant of x is equal to 1 over sine of x. So I'm going to have the limit of 1 over sine of x times, and then this is kind of a weird deal. It's sine of x with its input being sine of x. So it's kind of weird. And then I want to remind you back of this property that we have because it's so crazy, and I am going to have to use stars because otherwise you're going to be confused. Otherwise I'm going to be confused, so I won't even blame you. And so the limit of star going to 0, and this would be of sine of star divided by star equals 1. So all you have to do is make sure that you have stars in all of those places. The same thing in all of those places. That's what you need to make sure of. So when I look at this, I have the limit as x goes to 0. And what I have here is sine of x over sine of x, right? If I just put together what I have. So this is my star. That's my input right there, right? And look what I have in the denominator. Oh, that's what I wanted, right? Now all I have to do is make sure that out here I have that as well. And so really, I don't want this to be x goes to 0, but I want you to think about it as x goes to 0, where is sine of x going to? So if x is getting closer and closer to 0, well, sine of x is getting closer and closer to 0. How can I prove that to you? I know that's true, and maybe you know that's true too. And how would I prove that to you? I'd have to whip out my unit circle, probably. And so my unit circle. And I have an angle right here. And this is my x right here. And y'all remember that the sine is your y value of the ordered pair, right? And so I'm getting closer and closer to x being the angle there being 0. And as I do, the from both sides, right, from both sides, the y value is getting closer to this ordered pair that you would have at the end point here. The y value is what we're interested in because that's what sine is equal to. And it's getting closer and closer to 0. So maybe that proves it. I don't know. I hope so. And so this is sine of x goes to 0. And now I have exactly my property. And my property said that if I have this, it's equal to 1. And now you see that I do have that. I have sine of the star. The star is sine. So I'm letting star be sine of x, right? And then this is the star right here, right, going to 0. So this is equal to 1. I know that one wasn't very exciting. But anyway, so that's kind of the story on that.